Golden Iris Productions presents a multi-scale action-structured framework relating gravitational and electromagnetic acceleration. Part 1. Based on the paper by Mark F. Dennis. Abstract. The apparent incompatibility between quantum mechanics and general relativity has long been regarded as one of the central unresolved problems in theoretical physics. We present a structured comparative framework of three acceleration models: classical, electrogravitic, and emergent, applied across both macroscopic gravitational systems and microscopic quantum hydrogenic systems. Without simplifying or reducing structural components, each formulation is analyzed as an action-structured representation of force mediation across scale regimes. Gravitational and electromagnetic acceleration expressions are compared to identify shared structural components, including inverse power spatial dependencies, vacuum response parameters, and coupling constants associated with field interactions. Across both domains, geometric normalization factors, vacuum mediation quantities, and source-dependent coupling terms appear in structurally analogous roles. This work investigates whether these repeated correspondences suggest a deeper shared action-based framework underlying both gravitational and electromagnetic interactions. In this view, gravity and quantum electromagnetic behavior may be interpreted as scale-dependent manifestations of a common action-structured field system characterized by vacuum-mediated coupling and geometric dispersion constraints. Introduction. Modern physics is built upon two highly successful yet fundamentally distinct theoretical frameworks. General relativity describes gravitation as the curvature of spacetime induced by mass energy, while quantum mechanics and quantum field theory describe electromagnetic and subatomic interactions through discrete field excitations and probabilistic dynamics. Although each framework has been experimentally validated within its respective domain, their underlying mathematical structures remain difficult to reconcile within a single unified theory. A persistent feature across both gravitational and electromagnetic systems is the emergence of inverse power spatial relationships, particularly inverse square dependence, along with the appearance of universal constants governing interaction strength and propagation through the vacuum. These recurring structures motivate comparative analysis, in which gravitational and electromagnetic acceleration laws are examined not as isolated results, but as expressions of a deeper structural framework. In this work, three distinct formulations, classical, electrogravitic, and emergent, are applied to both macroscopic gravitational systems and microscopic quantum systems. Rather than simplifying these expressions, we retain their full structural content and interpret each term as contributing to an underlying action-based mechanism. The goal is to identify structural correspondences across scale regimes and to investigate whether acceleration itself may be understood as arising from variations embedded within the equation's constituent components. Fundamental structural components and their action roles. The framework developed in this work is constructed from a finite set of recurring physical and geometric components appearing across all six acceleration formulations: classical, electrogravitic, and emergent, in both macroscopic and microscopic regimes. Each component is interpreted not merely as a constant or parameter, but as an active contributor to the shaping of space-time structure through its role in governing interaction strength, spatial dispersion, and vacuum response. The gravitational coupling, universal gravitational constant G, defines the large-scale curvature response of spacetime to mass energy, establishing the baseline strength of macroscopic gravitational acceleration. In the electromagnetic regime, the Coulomb constant K and charge term Q squared replace G and M of mass, encoding interaction strength through electric field coupling rather than mass-based curvature. The vacuum permittivity, epsilon naught, and permeability, mu naught, act as propagation mediators, defining the impedance and response structure of spacetime to field transmission, thereby regulating how both electromagnetic and gravitationally emergent effects propagate through the vacuum. Geometric normalization factors such as 4π arise from spherical symmetry and represent the isotropic distribution of field lines in three-dimensional space, effectively encoding spatial dilution of interaction intensity. Radial terms such as r squared and r cubed define the dimensional decay and localization of fields, with r squared corresponding to distributed inverse square propagation in classical regimes, and r cubed corresponding to enhanced localization and gradient amplification in quantum and strongly curved regimes. Planck scale structure, represented by Planck length squared, introduces a fundamental discretization scale linking spacetime geometry to quantum gravitational limits, while the fine structure constant, alpha, governs the intrinsic coupling strength between electromagnetic interaction and vacuum structure. The electron mass, me, provides inertial resistance at the quantum level, balancing the strong electromagnetic charge coupling Q squared and defining stable bound state behavior. The Bohr radius, A0, functions as an emergent geometric constraint, encoding within a single length scale the combined effects of epsilon naught, Q squared, electron mass, and h bar, the reduced Planck constant, thereby replacing explicit fundamental constants with a stable equilibrium parameter in the microscopic regime. The local permittivity deviation term, 1 minus epsilon naught over epsilon local, represents spatial variation in vacuum response, introducing gradients in effective field propagation that modulate acceleration strength across regions of differing energy density. Collectively, these components define a structured action framework in which spacetime curvature and field-induced acceleration arise from the interaction between coupling strength, inertial resistance, geometric dispersion, and vacuum response. Across both quantum and cosmological regimes, differences in observed behavior are interpreted not as fundamentally distinct forces, but as scale-dependent reorganizations of the same underlying structural components, with variation in their relative weighting producing the observed transition from distributed gravitational fields to highly localized quantum interactions. Acceleration frameworks across scale. Macroscopic gravitational cosmic regime. In the classical formulation, gravitational acceleration is given by acceleration macro classical equals gm over r squared, where g is the gravitational constant, m is the source mass, and r is the radial distance. This expression encodes both the coupling strength of the gravitational interaction and the geometric dispersion of influence over spherical space.
The electrogravitic formulation introduces a vacuum-dependent structure. Acceleration macro to the Eg index equals 1 over 2r epsilon naught u naught times 1 minus epsilon naught over epsilon loc, in which acceleration depends explicitly on vacuum permeability, a propagation permeability parameter u naught, and a local variation of permeability term epsilon loc, representing a deviation from background vacuum conditions due to time dilation and a time gradient existing spherically around particles of mass.
The emergent formulation incorporates quantum scale parameters into the macroscopic expression. R macro to the Em equals 4 pi Lp squared Rme over epsilon naught U naught squared Q squared R squared, where Lp is the Planck length, alpha is the fine structure constant, Q is Coulomb electric charge, and Me represents an effective mass-energy coupling, in this example, the mass of the Earth. This expression preserves inverse square structure in radius, while embedding quantum and vacuum parameters of permittivity of free space, epsilon naught, and the permeability of free space, U naught, into the acceleration field.
Microscopic atomic quantum regime. At the atomic scale, acceleration within the hydrogenic system, hydrogen atom, can be expressed in classical electromagnetic form as A microclassical equals kq squared over MEA0 squared, where k is the Coulomb's constant, q is charge, Me is the electron mass, and A0 is the Bohr radius of shell n equals 1, the ground state or lowest energy level an electron can have in orbit around an atom. The electrogravitic formulation extends this structure by incorporating vacuum variation. A micro Eg equals 1 over 2r epsilon 0 u0 times 1m minus epsilon 0 over epsilon log times 1.99964 over r squared, which combines the same vacuum response kernel seen in the macroscopic case with an additional radial scaling factor reflecting quantum confinement. Finally, the emergent quantum expression is given by A micro Em equals q squared over 4 pi epsilon 0 MEA0 squared, which retains the same structural components, however inverted, as its classical counterpart, while emphasizing symmetry normalization and vacuum mediation.
This section introduced the 3 acceleration models examined throughout this work. First, the classical model, which describes acceleration using established gravitational and electromagnetic laws. Second, the electrogravitic model, which incorporates vacuum response and local variations in permittivity and permeability. And third, the emergent model, which embeds quantum scale structure directly into the formulation of acceleration. Each of these models is applied consistently across both macroscopic gravitational systems and microscopic quantum systems. This unified application allows us to compare how the same structural components behave across vastly different physical scales. Up to this point, we have established a structured framework for analyzing acceleration across both gravitational and quantum domains. We introduced 3 distinct models, classical, electrogravitic, and emergent, and applied them consistently across macroscopic and microscopic regimes. Through this comparison, a clear pattern has emerged. The same structural components, coupling terms, spatial scaling, and vacuum parameters recur in every formulation, regardless of scale. Rather than representing separate forces, these equations suggest a shared underlying system whose behavior changes through the relative weighting of its components. In Part 2, we will extend this framework further, examining how these structural correspondences lead to a deeper interpretation of acceleration as a gradient-driven process rooted in vacuum structure and energy-time variation. To be continued.